All right, it's 4 o'clock, so maybe we should get started soon, which means right now. So welcome everyone to lecture 3 of CS 545. So today is on probability review. So some logistical things. So homework 1 is out, so hopefully many of you have made some progress on that. Just look at Piazza, and then there's a post where we have links to all the assignments. So submitted on Gradescope by the deadline, although you do have a late day budget, but ideally you don't use it all on the first assignment. And you'll see from the homework that there is a question that I have about which resources you use to work on the homework. Make sure you answer that. Even if you didn't use anything, you have to say you didn't use anything to get full credit for that. Yeah, question?
How many members do you have?
It groups of around, let's aim for around 4. If you're at 3 there's no one left, then we can, maybe 3 is okay, but let's try to get 4 for the lab. Yeah. And yeah, speaking of the lab, so the lab is, well, one of the TAs released the lab basically a few minutes ago. So I'll get the link, I'll get it on Piazza with more details by tonight. So it's not due until February 2nd, and the lab should also not take 2 weeks to do it, mostly just to make sure that you have your team set up, you have your Ubuntu operating system with ROS all set up, and then you can run that stuff. And so next lecture we'll have a little bit more about ROS and getting that set up. So yeah, so logistically, just make sure that you try to find a lab team by this week. If you're having trouble with that, then ask around on Piazza, or you can ask the instructor, and then we can try to maybe merge some teams if we need to. Yeah, so again, the first lab is mostly just about making sure that you have ROS all set up. So it shouldn't take 2 weeks to do, but we just give you that time because the setup cost might be longer than expected. And my general rule with working with software is to always overestimate how much time it takes to get things set up. Yeah, and then I'm gonna try to change something a little bit with the lecture structure. So we'll try to have maybe like a 5-minute break in between the lecture, like halfway through the lecture. So we'll see if I remember to do that. And yeah, if I forget, just let me know. So any other logistical questions? And I do have the my iPad with the Google Docs. So if you don't want to raise your hand and you prefer to type something in, I'll look at this. But I don't see anything here yet. All right. So before I get into some more details, I also want to mention some best practices about working with lab teams, because you will be having a team of 3 or 4, ideally 4, but maybe 3. So we will ask to make sure that each team member contributes to the lab. So the main thing is that I just wanted to make sure that there wasn't anyone who just refused to work and then left everything to like maybe one person in a team, because I feel like that wouldn't be fair. So I want to make sure that everyone in the lab team contribute somewhat. So for some best practices that I've observed, so just try to make sure that you have a lot of communication between the lab members. Do try to document who worked on which part. So don't share account, like don't share any personal account, but do make sure that you're documenting who worked on which. I also don't recommend trying to divide by tasks. So like have one person write one script and then the other person writes another one, because the problem is that there's a lot of interdependencies among scripts. So it can get pretty tricky to do that. And this is also the same tip that many other classes that I am aware of that also have group team, they suggest that policy as well. And I would say don't worry too much if you feel like there are very minor differences. So if you feel like you did maybe 20% of the work, whereas everyone else did like 25 or 30%, then that might be okay. I'm more concerned about if someone just decides not to do anything. And so I just want to make sure that everyone contributes, and then there will be a question about that in the lab report. And yeah, and if you do feel like you haven't contributed too much, then maybe you can offer to volunteer to do some extra work, like maybe do more of the writing, for example, of the actual report. Although the implementation is more important than the writing from a credit assignment scheme. Yeah, if you have a concern just about the group, the course staff can try to help. So, all right, so let's get into the material for today. So this class is about probability. So the math that we cover, hopefully a lot of it is review. But you might also be thinking, well, why are we studying probability in this class? I mean, if you saw from the class website, we have a textbook named Probabilistic Robotics. And really the motivation here is that if we want robots that operate in today's world, then very often we're going to have partial or noisy information about either the robot itself or especially the environment that it's in. So whenever a robot is like, maybe it's outside and trying to traverse or navigate through some roads or terrain, it'll have maybe a camera that captures the image of what it sees, but it's not going to capture everything. There might be like occlusion of something really important. There might be other things missing, or maybe the camera is just noisy. There's always some amount of noise in sensors. And you also might get stochastic dynamics. So what I mean by that is, think of a robot and having it take an action. So maybe it moves forward by 1 meter, or maybe it's a manipulator that tried to move its gripper somewhere. When you tell it to do that, there's always some noise, like some robots are just imprecise. You tell it, move forward 1 meter, and then move forward 1 meter and 1 centimeter, 1 meter plus 1 centimeter. That can be a problem if you're dealing with like things that really need high precision. And things get even worse when we have like robots in clutter. So a robot that's trying to grip a bin of objects. There's a huge bin of like various objects that you might see in an assembly line, and then the robot manipulator goes in, and then when it goes and touches stuff, what are the objects going to look like after that? If there's a lot of clutter, it makes it really hard to predict that. So that's what I mean by dynamics are stochastic, and they can be hard to write a mathematical rule for. So the advantage here of probability is that we have a framework to try to reason about all this. So we have a distribution over possible states of the robot and the environment. And we also have distributions of possible outcomes. So if the robot does something, then we have a distribution over what the environment looks like after that. And we might need to know that, like if we want the robot to do something, then ideally we should know that if it's gonna move its gripper and then do a pick and place, we want to know what is the object going to look like after that. So we have some kind of distribution here. So part of the reason why we also study this is, the motivation of many people who work in robotics is also to try to get robots that work in a less structured environment. So it's possible to reduce the amount of noise that you have if you restrict your robot to be in factories, and then they do the same thing over and over again. But I would argue that much of the dream of the robotics community is, get robots out in the real world, like interacting with people and in situations never seen before. Personally, I would be excited about that. So let's look at this video. I like this video. It's from Peter Beal and Andrew Ng. So back when Peter Beal was a PhD student, he did a lot of work with autonomous helicopters. So they would try to program this helicopter, do the fancy maneuvers. And what I want you to get out of this video is less about the specific helicopter techniques and more about understanding, like, what are the challenges in doing this? for example, if you try to, assume that we have a sensor that tells us what's the robot's position. Well, there's, again, if you ask the sensor to give you the robot's position or the robot like velocity or whatever, it'll give you a noisy estimate of it. And whenever we have other, maybe optical or unexpected things like wind that changes things, then it complicates how we can, track where the robot is and what action it should do to perform the maneuver. Yeah, so we won't be doing helicopters in this class, but again, the main takeaway is to think less about the task and more about the common challenges that many robots face, or many robotics face when they try to control robots. So let's talk about some terminology. So the word state is something you'll see a lot. So state is basically, and the definition of what probabilistic robotics uses is like it's information about the robot and the environment that could impact the future and which the robot uses to make decisions. And that's one terminology. I think another way to think about state is a condensed ground truth interpretation of where the robot is, or where important stuff in the environment is. So state is often a term that we use to condense that complex helicopter environment into just the things that we care about. So if we only care about the state of the helicopter, then maybe there's just a couple of numbers that we have to keep track. Maybe position, orientation, velocity, and angular rate. So in order for us to get those things, we need some kind of sensor. And the sensor will give a noisy estimate of the quantity. So let's say you have a GPS sensor, and it'll give you some estimate of position, plus or minus some amount of noise. There's also inertial sensing units that give you, again, noisy estimates of other quantities like angular rate, acceleration, and so on. And then from a dynamics perspective, there's wind and there's unmodeled dynamics in engine that we often ignore or we have to approximate. And all of those things make controlling the kind of robot more challenging, and which motivates the need to use probabilistic reasoning. So I see someone typing in the question, and is it safe to say that the sensors give an estimate of the state? Yeah, that's how I would interpret it. Yeah. So you have sensors that give you like observation of the state. So, oh yeah, so our second example is a mobile robot in a home. So this is one where we've been, I think the general public has been trying to clamor for robots in the home, but they're not there yet. And some of the challenges in that are that, well, let's suppose that we just condense the state to just be position and the direction where it's facing. Then you still have noisy sensors, like you have odometry to sense the motion of actuators, you have laser rangefinders for measuring depth, but they'll always give you noisy estimates. So the way that, for example, laser rangefinders, the way that depth is generally estimated is you have some kind of camera, it shoots out a light beam, and then you measure the time that it traverses to go to the object and then to go back. And then you can use that to determine the distance, which is depth. But there's always some noise in that. Like if you've ever worked with depth cameras, you've probably seen a lot of holes in them when they don't accurately reflect the depth. And then there's many other problems with these kinds of sensors. And yeah, and then dynamic uncertainty, what happened when a wheel unexpectedly slips? Or maybe there's unmodeled variation in the floor and other surfaces, or maybe there's like, adversarial humans or pets around that, that affects the state or the robot. Fine. So probability theory axiom. Yeah, so hopefully all this is review. So just like most of last lecture, so if this is not reviewed, then just make sure that you go through the material then and try to make it feel like review. So the probability, it I wrote here the language that speaks about the likelihood of events. So you have a universe of atomic events where things that could happen or ways that the world could be, and we start from axiom that we assume are true. So that's like many fields of math. You start with axioms and then other properties, you deduce them from that. So some of the axioms that we'll assume are just true are that like the probability of 2 is 1. Or the probability of the universe. So that's what I mean by U. So you'll see some other references. They might use like omega or other symbols, but this is basically saying that among all the events or the universe of events that we're considering, this is like, no, this is the set of events that we're considering. And the probability of the whole thing is just 1. Because if it's not 1, then it's not like the proper universe of events that we're considering. And of course, if you have the probability of being false, that should be 0, which is also the same as the null. Yeah, question in the back. Yeah, what we don't know what the question is, sorry. So your question is, I'm sorry, I'm having trouble understanding the question. So you're referring to likelihood.
Yeah, except that.
All right, so the likelihood of an event occurring, there is the term likelihood is used in probability. I think we're interpreting it as the same thing, like the likelihood of an event occurring is the same as like the probability of an event occurring. For now, I would just assume that those two terms are equal. I think the term likelihood is not going to appear today, so I think this is not something to be worried about right now. Yeah. Yeah. But generally speaking, whenever I say like, P of something, it's like the probability that this thing is true or the probability of this occurring. Yeah, so some of the other axioms that we can assume are true is that whenever we have the probability of some event, or maybe the probability of a set of events, that probability has to be between 0 and 1, right? So it doesn't make sense to have negative probability. And the probability, if it's equal to 1, that means it's always true. So you can't really go more than that. And visually, if you want to look at it, U represents the universe of all possible atomic events that we care about. And A and B are different sets here. And you can think of each location in this box as one example of an atomic event. And so if we have to think about the probability of like A union B, or in other words, you can also think of it as like the probability of A or B occurring. Then you can add up the probability for each of A and B, but then you also have to subtract their intersection because otherwise you're double counting here. So yeah, so this is another set of axioms that we just assume are true, and then we'll derive our other property from that. Any other questions on this like Venn diagram thing? This is similar, I think, to one of the homework questions where you have to make like your Venn diagram. So yeah, so when you're starting from the axiom, you can use them to derive a new conclusion. So if you look at this is what this is saying is the probability of A union with U set minus A. This is another way of writing like the complement of A. So that's this thing like all the events in the universe that are not in A. You'll just assume that they're in A complement. So the probability of A and or A complement is the same as the probability of A plus the probability of U set minus A minus their intersection, which is the same as, it's the same as this thing, except B is just A complement. Yeah. So you just plug in A complement here. And similarly, you can also derive other axioms like P of U, the probability of the whole universe, is the same as probability of A plus the probability of A complement minus the probability of null, which is 0. And something similar for the third conclusion. Hi, random variable. So a random variable is this mapping from a discrete domain to a range from, 0 and 1, if we're thinking about probabilities here. So the probability of any particular case of a discrete random variable equal something cannot be negative or more than 1. And then if you consider their domain, they just sum to 1. So notation, you'll often see X or, X is the default like no variable for a random variable, but sometimes you'll see Y or sometimes you'll see A or B. So X can take on a countable number of values here. So like X1, X2, all the way to Xn. And then you have probability of that X is equal to Xi, which we often shorten as P of Xi. So that's the probability that the random variable X takes on value Xi. So you'll often see this notation. So just be aware that this little p notation is shorthand for this like capital P notation. Yeah. And more formally, P is a probability mass function. So what's an example? The event that it is raining in Los Angeles is a random variable. So the domain would be true or false. Maybe the probability of raining equals 2 is 0.8. And the probability that it's not raining is 0.2. Is this a valid probability distribution? I mean, to me, it's a valid probability distribution. It might not be a very accurate model of what it's actually like in living in LA, but it is a valid distribution. You have two events and the probabilities are non-negative and they sum to 1. That's all we need. Fine. So when we're dealing with robotics, we often need to deal with multiple random variables. So why is that? Well, you might have different parts of a robot, like different sensors. You have battery and light, and you might have random variables that associate to each of them, like the status of the battery and the status of the light. And so what over here is what we call a joint distribution between two random variables. And this is a joint, so it tells you for each battery and light, what is their probability. This is what happened when we marginalize it out to just get the probability of a single random variable. So hopefully it's clear how to get this. Like for the battery low, you just sum up the 0.04 and 0.06. This is the same as like marginalizing out the light variable. Yeah. So 10 seconds. What's the probability that the light is off? I'll give you a couple seconds to think about it. So 0.05. So hopefully you all got that. Yeah, I see it in the I see it in the student question too. Yeah. Oh, I don't know if that was typed in before or after I share the slide. All right, conditional probability. So the probability of A given B, this is what we write it as. This is defined as the probability of A and B, or their intersection, divided by the probability of B. And no, the numerator is usually the numerator is written as P of A comma B, but we sometimes write the intersection if we're dealing with like 2 or 3 random variables, then it's simpler for us to maybe think about. But no, usually I'll write it with the A comma B notation. Yeah. So another way to think about this intuitively is that we only think about parts of the world where B is true. So P of A given B. So this thing basically means we restrict our analysis to this B, like where, the circle that represents B. And then that's why this is the denominator. And then we have their intersection, which is the numerator. So, probability of A given that, B is true. All right. So quickly, what's the conditional probability that the battery is low, given that the light is off? So I'll give you a couple seconds to think about that. Yeah.
0.04. Oh. About it, sorry.
Yeah, so 0.04 is the numerator, then you divide by the probability that the light is off. So the conditional probability is 0.8. So one reason why sometimes conditional probability can be intuitively confusing is that you can get high conditional probability even when like the probability that the battery is low is very low. So this is the same as the last slide where the probability that the battery is low is 0.1. But if you condition it on something that's also like low probability, you can actually get a high conditional. So yeah. And this is how to do the math here. So in other words, we just look at the column and then because that's when the light is off. Right. All right. One reason or one example where the conditional probability appears a lot, not just in robotics, but also in other areas, is with Bayes' rule. So Bayes' rule is the seemingly very simple equation which just says probability of A given B, probability of A given B and probability of B given A multiplied by probability of A divided by probability of B. Right. And you can always rearrange the term to reverse B and A. So if you can consider B given A, then you just have to flip where A and B are in this equation. Yeah. So hopefully all of you have seen Bayes' rule before. Now, one thing that you might be thinking about is, well, what is it useful for? Like, why is it useful? So in robotics, we often have these observational data from sensors that try to measure what is the state. So I was talking about what a state means, and we tend to want to know like what is the state of the robot or what is the state of the environment conditioned on observational data that we have. So this might come from maybe some camera that tells information, but it's like a noisy reading of the state. But this probability is also very difficult. Like it's hard for us to think about the probability of a state, given that observation directly. But when we use the decomposition, it can be a lot easier. because probability of state, people call that a prior probability. So we might have a prior knowledge or some data about the likelihood of certain state. This thing here is like probability of observation given state. And you can sometimes get that information just by counting frequencies or just getting some data, like when you test out a sensor. So let's say you test a camera, you put a robot and object in known configuration, and then you take pictures with the camera, and then you get your observation. And that can give you quantitative data that you can use for this numerator. Oh, so I see a question saying, how do you get the prior probabilities of the state? So that is a good question. There's no right answer there's no right answer for that. So sometimes it's just some experts will use some assumption that they have about a problem domain to assign a prior distribution. Yeah, so if you've taken like machine learning or statistics and you had to deal with prior probabilities, you're often just given that. Or you can also just assume a very weak prior, like a uniform distribution over all possible states. Yeah. So you might also be wondering about the denominator. So normally we might not care too much about the denominator. In fact, you'll often see that you'll see later that many people write this formula as using the proportional to symbol instead of just like actually computing the observation. So the denominator is just something to normalize it. If we only care about, a set of states of the robot, we can just, go through all the states, find which one maximizes that probability, then that's just the one that we use. Yeah. So if you're like more of an optimization person, sometimes you'll say like argmax of, the set of states, and then you just have to compute the two terms and then in the numerator because the bottom one will stay the same because you're conditioning on the same observation. Yeah, and we'll see many examples of Bayes' rule this lecture, then next week as well. All right, independence. So A and B are independent if and only if the joint probability can be factored into the product of their individual probability. So in other words, probability of A and B is equal to the probability of B of A, or B times the probability of A. The ordering doesn't matter. I said B first, so that was actually a good lesson because you can commute these and it doesn't matter. So another intuition for this is that knowing that B is true doesn't give us any more information about random variable A. So you can also write it as probability of A conditioned on B is just the same as probability of A. And same thing if you reverse the ordering of B and A. So temperature and time of the day. So you have two random variables. Yeah, so temperature and time of the day. And I would argue that those are not independent events. So why is that? Actually, I'll let you think about it. Like, why are these not, why are these not random? Why are these not independent? Because like, if you know that the time is in the evening, then the temperature gets lower. So now stuff like that. And mathematically, it will simplify things. So, whenever you have this, if you have math like this and then you simplify it like that, you're making a strong assumption. It might simplify the math, but you also want to be careful that it's actually true. So if you think about it, it can be very difficult to think about treating different random variables as different robot sensors and thinking that they're independent, because when you have a robot with a sensor to try to understand like something about the state, it's probably not going to be independent, because if it is, it's also not very helpful. Does the last bullet point make sense? Like if you have a sensor and you're trying to understand something about the robot, then it shouldn't be independent. It should be like heavily correlated with, what where the robot is. Right. Right. So that was independence. Sometimes we also call it absolute independence. This is conditional independence. And for a reason that you'll see maybe next week as well, conditional independence is very important. So A and B are conditionally independent given C if the following holds true. So there are two different lines, both of them, they basically define what conditional independence means. So you can just start from this and then derive the second one, or you can start from the second one and derive the first. So the intuition is, if you know B, but you're also conditioning on C, then B doesn't give any more information. So you might have three random variables, A, B, and C. I like to think of it as this. You can factorize it as probability of A given C times probability of B given C. So normally, if you remember your factorization rule for probability, you would have to write in P of A given B comma C. So you would have to condition on B in addition to C if you didn't know that they were conditionally independent. So, and one of the main takeaways is just to remember that conditional independence does not imply absolute independence. So you have three random variables, two are conditionally independent. Given the third, don't assume that the first two are independent. So in general, it's not true. So one example is, C is like some weather condition. So people like to use raining for some reason as an example of random variable. So we'll just go with that. So C is a random variable about raining, and then A and B are other random variables that somehow relate to it, like the probability that someone holds an umbrella when they're walking, or the probability that, the floor is wet or something. So normally those are not independent because if people are holding out umbrellas, it's more likely that the floor that they're walking on are wet. But if you condition on the fact that it's raining, maybe that explains everything. So, yeah. Any questions on conditional independence or normal independence? All right, so we just covered earlier discrete random variable. So now we'll cover continuous random variable. So instead of having a finite set of possibilities, you just have something that's continuous, like position of the robot, where each coordinate is a continuous value. And so in this case, you cannot think of a random variable as being equal to a singleton thing. You have to reason about interval. So the probability that X lies in some interval, A from B, that will be the integral from A to B of P of X. So intuitively, just think of it as like an area under the curve. So this is these are a set of probability density functions of the Gaussian distribution. You'll see a lot of that later today and later in this course. And these all satisfy the property that we need for probability density functions. Like you need to make sure that they're non-negative, that they integrate to one, and they're piecewise continuous. So because they integrate to one, you have to make sure that the area under the curve for like each of these is exactly one. Yeah. And yeah, so quick question. So these are a set of density function for different parameters of the Gaussian distribution, you'll see that they're all below one here, right? Like they're the one here. Could there be a density function that goes above one in some areas? Like, can you have a density function that in some areas it goes above one? Yeah, so I see some yeses. So yeah, and the reason is that and you can go above one as long as you shrink other areas accordingly, so that the area under the curve is exactly one. Because that's what matters. Yeah. Sometimes like just be careful if you're like debugging code and you see P of something is 2. And you think, well, you can't have a probability of 2, but that's not the right way to think about it. What you're really saying is the probability that it's in an integral. Like, and then you have to integrate over something. And then that will shrink that'll shrink your probability thing. Yeah. All right, quick example. Is this a valid probability density function for a random variable? I'll give you some time to think about it. So this example, I actually remember this example from one of my undergrad math professors. This was 12 years ago. So I remember his example. Yeah, so again, I'll give you a few more seconds to think about it. Say maybe 20 more seconds. All right. What do you think? So someone wrote it, I don't think it integrates to 1. Do you agree with that? But well, first, before we get to that, let's look at some of the other conditions. So it's piecewise continuous and non-negative, right? Because by piecewise continuous, I just mean that like if you have intuitively different pieces of the function on the real line, they're all like continuous. And that's true here. And it's also non-negative because you can factorize this into this term. And then it's like whenever like you can go through the different combinations of this, but like if x is say like below if x is greater than 1, where the first term is negative, then this other term is gonna cancel out that, then you'll get something that's positive or non-negative. All right, so this is the formula for how to do that integration. Yeah, and if you do the math, you just integrate from 0 to 1. You don't have to go beyond the other range because it's 0 there. And then when you compute the antiderivative, it's like 2x. You just go term by term, like 2x, 3x squared over 2 minus 5x cubed over 3, and then you get 11 over 6. But if you multiply the function by 6 over 11, then it would integrate to 1. So, all right, so So someone is asking about piecewise continuous, then for x just below 0, the value is 0, but for x equals 0, the value would be 2. Well, all right, you can have sudden jumps. So like, for example, if you have like a uniform random variable, it has like if you plot the density function, it's like a flat line, and then it jumps to 0 at the boundary. So you can have like different jumps there. So I think there's a mathematical way to just precisely describe the piecewise continuous part. Like in general, we won't have to worry about technicality of that form. Yeah. So hopefully that example is clear. So usually when you're dealing with functions like that, the condition of not integrating to 1 is easy to fix if it's just a matter of multiplying by some constant to rescale it. All right, the normal distribution or the Gaussian distribution is very important. I mean, you would think that something that is named normal distribution is very important. So you parameterize them with mean and variance. So basically, once you know those two things, that sufficiently describe everything you need to know about that Gaussian. So we'll write it as n with x for different values that x can take on in the real line, semicolon, mu, and sigma squared. Yeah. And this is the probability density function. So this is the formula that you'll see basically everywhere. It's the density function for the Gaussian, where the first term here, the one that raised to the -1/2, that's just a normalizing constant. And then this part is the real key thing for that distribution or the density function. And I repeated this thing here. This showed different density function for different parameters. So if you look at mu, where mu is 0, that means you center the Gaussian around 0. And so it has the highest value at that point. And then how wide it is based on the sigma value. Like the larger sigma is, sometimes the fatter the distribution. But of course, since everything must integrate to 1, you also have, whenever you widen the distribution, you have to lower the peak, and vice versa too. Yeah. And hopefully you see that. Yeah, question?
Why is the normal distribution so special? Why is this that is that?
Oh, well, if you're aware of what the central limit theorem is, then it shows that very informally, whenever you have different sums of different random variables and you're trying to consider the distribution of that, then that is basically a normal distribution, even if the random variables were not normal. So normal or Gaussian noise is often prevalent in when studying different fields too, like different random variables or other phenomena that you're observing. So what I said is very informal. If you want the more formal explanation, you'll cover it in statistics and probability courses. Basically every reasonable probability course will have a discussion about the central limit theorem. So yeah. And hopefully everyone sees why the distribution is shaped like that. So if you look at the numerator, it's x minus mu. So if x is equal to mu, then this whole thing is 0. It's e to the 0 power, right? When you make x further away from mu, because you're squaring here, this thing is always going to get increasingly positive. This x minus mu part will get much larger. But because you have a negative here, it'll be like e to the negative power, which means that 1 divided by e to the positive power, which means it goes to 0 quickly. And so that fast decay is why you see something like that, it decays so quickly. So technically, it never exactly zero. Like there's always, it's technically unbounded, though there is some, no, you can plot the normal distribution density function and it'll be non-zero everywhere, but in practice, it's basically zero for all intents and purposes once you get, far enough away from, from the mean. All right. So let's just recap a few formulas here. So making sure that we're all aware of it. So some important formulas to be aware of are whenever we're trying to marginalize out or remove one variable, then you have to do something like this, where this thing is the same as the joint distribution of P of X and Y. And by summing out Y, you're marginalizing out Y while keeping X what it was. So this thing is the same as probability of X. Yeah. And if you're in continuous land, you have to make sure you integrate. So all the sums become integral, then you have to put in dy at the end, or dz or whatever you're integrating over. Other thing to be aware of when you're conditioning, we remember that we talked about Bayes' rule where we had like P of X comma X given Y is proportional to P of Y given X times P of X. If you really want to explicitly write what is in the numerator, which normally you don't have to, so don't worry if you don't want to remember all these, but if you do want to write it out explicitly, then you have to do something like this, where you kind of take the probability of Y and then you plug in like what is at the top in the numerator in the denominators here. And then the reason why we just use x prime is just to make it a little bit distinct from the x that we're actually considering here. Yeah, so hopefully all these formulas are, you know them, and then you can maybe use them as a reference or maybe put them on your cheat sheet for the midterm. All right, log total probability. So from the last slide, we saw that we have P of X is equal to this thing here, where this is the joint distribution. I just factorized it into P of X given Y times P of Y. You can condition on more things. So let's say you have Z. As long as the general rule is like, as long as you add in Z everywhere in the conditioning, it'll be okay. So you see, we condition on Z here, but then we put a Z here and a Z here. So it should just go in like all three of the terms that you see here. Yeah, so sometimes when I go through the math and to verify that formulas make sense, like I'll often just try to mentally block out everything that is being commonly conditioned on, and then I'll add in all the conditioning later. Yeah, so I find it helped me to think about these, especially when we get to probabilities of like, many more things. Yeah, and then same thing with Bayes' rule when we're doing the conditioning, so we can condition on more things. So again, just be consistent and put a Z and condition on it for every term that you have. And Z, you can also think of Z as like a tuple where you have Z equals Z1, Z2, all the way to Zn. It'll be fine as long as you're consistent in where you're conditioning. All right, expectation. All right, so before we actually move on, I did promise that I'll try to experiment with like taking a short break in between the class, in between in the middle of the lecture. So let's take a very short, a few minute break for now. And if you have questions, I'm happy to try to answer them. But let's just take a short break for now, and feel free to walk around and, just come back in like 4 or 5 minutes. It's the same as last week. I think the battery ran out too. Oh. Wait, you have a question? Okay, is it that you're waiting for a unicorn? Hey, you can. Yeah, you can try to find a latitude and. I think we try to find a latitude, but you often but you found one, then I think that you can still. So we can help you as. All right, so you probably get started in a few seconds. We'll get started again. All right, so hopefully everyone had a good break. It'll get quiet soon. Okay. All right. Expectation. Yeah, so again, hopefully you have all seen this before, but we'll just get a little more practice and a refresher on expectation if you need one. So, expectation. You have different definition depending on whether your random variable is continuous or discrete. So this is the way that I write out what an expectation means. So like E of X is the same as you're summing over all possible values of X weighted by how often they occur. And something intuitively is similar when you integrate, like you have to integrate over X with the weighting term based on the probability or the density function of X. Yeah, so again, the intuition is, it's kind of like an average or like what is like an average of this random variable. And hopefully everyone has seen linearity of expectation. So this is a very useful property that for any two random variables, you can split up an expectation into ax plus by, where x and y are random variable. You can split it up like this. And you don't need the random variables to be independent. And the really nice thing is it works out very well when you're doing math to simplify things, and it assumes basically nothing. So that's what really makes it very powerful, because it has basically no assumption and it can be widely applicable. So oftentimes when you're doing math with expectation, you've probably seen a case where linearity of expectation helps you. Right. Example of a discrete expectation. So what is the expectation from this random variable that is like when you roll a dice, you get some amount of money or you lose some amount of money. So what is the expected value of money that you get? I'll give you a couple seconds to think about it. Hmm. I see one answer. Yeah, I see one. I see one answer here. Uh, hopefully everyone got it. Uh, so when you have something discrete like this, it's the expected value of all these outcomes weighted by this thing. Now, because we have six, there's technically six different things, but they overlap here. So if you have one or two, you get the same amount. So really, we have like three different things happening, each with their own weight. And so this is basically how you do the math. So minus negative $3 with probability 1/3, $2 with probability 1/3, and $5 with probability 1/3. And if you add it up, you should get that. So, yeah, I saw it here. So it's pretty good. Yeah. All right. Continuous expectation. Assume that X is the time that the battery of a robot lasts, and that it follows this probability distribution with a density function like this. So for X between 0 and 50, it's 0.02. And if you do the math, like it's 0.02 times like 50, you'll get like 1, basically. So it integrates to 1. So what is the expected battery life of the robot? I'll let you think about it a little bit. Trying to get it. Oh yeah, don't forget the density function is 0.02x. So I'll give you maybe 20 more seconds. And don't worry, if it's like, if you get the algebra up to the point when you have some complicated arithmetic, you can just leave it, you can just get the algebra to be like the close to the like a final thing. Up to if you had a calculator and wanted to do it. But generally, we're not going to assume that you need to use like a calculator or these days. I don't. Do people use calculators these days? I don't even actually know because I don't even use them. Does everyone get this? So if the expected value, this is just the definition. Like if you go back here, it's literally this thing. So you get this, and you pull out the 0.02, then yeah, you compute your antiderivative, and then you should still compute that. Okay, so all right, so I have a question. Is the probability density function valid here? The integration of this thing would be 0.01 x squared. Yeah, then yeah, I mean you would have to integrate over from 0 to 50. So yeah, yeah, I mean, if it doesn't, well, here's the thing: if it doesn't integrate to one, you can always add in some like constant or to change the range of the interval so that it actually integrates to one. Yeah, yeah. Although we will double check that everything actually integrates to one if we give you like a problem to focus on. Yeah. All right. All right. So this thing is a little more standard. So you have a uniform random variable. So you have x, which is drawn from uniform 0 to 1. That means it's like 0 to 1. It could be basically anywhere in the interval. And what is the expected value? So yeah, so this one is just going to be very quick. So x has range 0 to 1, and the density function is basically one in that range. So you do the math, and then you get this. So it's 1/2, which makes sense because if you're drawing uniformly from 0 to 1, then you kind of expect that your average is going to be 1/2, like in the midpoint of the interval. All right, Gaussian random variable. So let Z be a Gaussian random variable. Here it's actually a standard normal. So a standard normal is like mean 0 and standard deviation 1. The reason why we have all that is because you can always like normalize your Gaussian to be a standard normal, as long as you unnormalize it later when you need the actual numbers. So if you try to find the expected value, so Z has range, well, technically the range is minus infinity to infinity, but I mean, in practice, the density is basically 0 when you get beyond a certain point from the mean. And so normally people don't actually compute this math. I'm just mentioning it here because it's a common question that some people have had where if you actually try to compute the antiderivative, there's no nice antiderivative, but you can use things like, your own intuition that if you have a symmetric function around some centered at something, then the expected value is going to be at the mean, basically. All right. All right, variance. So variance, though, like with expectation, we have different definition for discrete versus continuous variables. So the variance is this thing here where you have x minus the expected value and then that quantity squared, weighted by the probability mass here. For a continuous land, it's something similar again, but you integrate and then you add in dx at the end. And the standard way that we write it with the sigma notation. So sigma squares, and then if you really want to be precise, you can put in like x as the superscript, but if you know what random variable you're talking about, you don't have to do that. So yeah, it'll tell us how much your random variable fluctuate about the expected value. Yeah, well, that's what the variance. And yeah, this very useful fact that this first definition, expected value of x minus e of x, expected value of x squared, this thing here is basically from the definition, right? So if you remember what the expectation was, you had this, if you're in discrete land, you had a sum over this x thing. You can change that to be a function of something. And then here the function is this thing here, x minus e of x squared. So this thing, you're just plugging that in here, then the first line is basically like the definition of the expectation. And then does everyone see how we go from the first line to the second, the third, and the fourth? So for the first to the second line, we just factorize it. So you can, I don't know what people call it, but you do your like first term of the first thing times the first term of the second thing, then that's your first term of the thing, and then do first term times the second term times the first term, second term times the second term, then you get this thing. How do we get from the second to the third? How do you go from the second to the third? Like, what do we use? So what's going on from here to here? Yeah.
Linearity of the expected.
Yeah, it's linearity, yeah. But there is one other thing here. So you have this thing here is 2 expected value of x times x, right? You're taking an expectation of that. Now, what happens here is that when you take in an expectation of a constant, then that constant pulls out, it moves out. And this thing here, expected value of x, even though it has a random variable in it, it becomes the constant once we cut it with an expectation. So just be aware of that, because this thing can get confusing sometimes, where you have, let me just write it out. So have, yeah, so when you have expectation of 2 times expected value of x times x, this thing is a constant, you can pull it out. And the same thing with this. So, yeah. Yeah, so I know someone typing in something, but I'd like to first leave you with this question as well while I look and see what look at the question. So if you have a uniform random variable from interval a to b, where a is less than b, then what is the variance? And then I gave you this to help. So maybe I'll just let you get a minute to do this thing. Oh. So I think the question was, can you explain the significance of that fact? So I'm not sure what that fact means. I think you're talking about this thing. So I assume that it's this thing. So the reason why this is helpful is because I mean, it helps us to we need that to simplify the math, right? So if we go from here to here, we need two different cases of E of X, right? We need E of X times E of X to get the whole thing squared as we do here. So yeah. Oh, okay, and then if you're wondering about this fact here, when you're working with math with variances, then often this thing is often an easy way to to simplify the math or something. There are different ways of expressing the same mathematical quantity. So when you're doing the algebra, yeah, sometimes one way is easier than the other way. So, this thing. All right, everyone got this? Maybe 30 seconds. All right, so to compute that, you can start from the definition of the variance. So if the integral from A to B of this thing squared multiplied by the density function. And it's really important that we are integrating from A to B. Yeah. You can go from negative infinity to infinity, but it's going to be zero like outside this range anyway. And then when you do the math, like the integrand will be something like this, where you can go through the math in your own time and verify the algebra, but it'll turn out to be something like b minus a over 12. Yeah. And like you can also double check on, like, I think Wikipedia has a whole bunch of pages on this random variable of this. And then because the expectation and the variance are so important, then it'll just tell you what it is. Yeah. All right, covariance. So the definition of covariance for the two random variable x and y is this thing here. So we write it as COV. Sometimes it's also sigma of x and xy. So the expectation of x minus expectation of x multiplied by y minus expectation of y. So it's kind of like the measure of the joint variability of two random variables. So yeah, and then just be aware of this thing. So hopefully everyone has seen covariance before. All right. So most of the time we've been working with things like one random variable or two or three, but we really have the general case to consider in robotics, especially when we deal with like multiple time steps, as you'll see later and in the next week and so on. So when we write out random vectors, then we'll try to be consistent, but sometimes it's hard because different resources, they use different, make different assumptions on notation. So this is just a case of being like mathematically mature and understanding that when like X is a vector versus like a single scalar or something. So we have X, which is you might denote it as X1, X2, all the way to Xn, where each of these is a random variable. Yeah. And again, from a robotics view, you might have many different sensors, or you might be dealing with time step where you have where Xi indicates the value that X takes on at each time step. So again, those are very common in robotics, so just get used to working with different random vectors. Yeah, so some of the formulas that you might want to be aware of are in order for f of x here to be a valid density function, you need to make sure that when you integrate over all the random variables, like all of x1 all the way to xn, you get 1, basically. And same thing when you write out the mean and the covariance. Well, the covariance we'll get to later, but the mean, so sometimes we'll write it with x with the bar, where you integrate over all of x1, x2, all the way to xn, and then you have to thicken your random vector here, basically. Yeah, then for covariance, this is really this is a matrix. So this is a matrix of value where each item in it is the covariance between one item and a second item, where each of them are like drawn from like the possible vector of items that you have. And if you remember that this is the outer product notation, you have this thing times this thing with the transpose, like it turns into a full matrix. Yeah. And so you don't have to, so I think generally speaking, you don't have to worry about like memorizing these formulas. We'll either give it to you or you just have to assume that, assume that it's going to be true if you're given a joint density function or something like that. So because Gaussian distributions are so important and because they involve a covariance matrix as part of the density function, I think it's also very helpful to have really good intuition on like what a covariance matrix is. So if you have a random vector, x1, x2, and x3, then if we assume that the mean is mu for each of these, so it's like mu is a vector with term mu1, mu2, mu3. This is basically what the covariance matrix is, right? So if you look at the definition, it's x minus x to the mean. That's what's going on here. You have this column vector, and then this row vector. It's the column transpose with the row vector. And you go from the first variable to the second one to the third. So, yeah. And then when you do the matrix algebra, you get something like this. So if you really want to do this by hand, and normally you don't want to do this for more than 3x3 matrices. So, but for this, just be aware of how you can actually write it out like this. And if you also want to simplify it even further, you can also just put in like B, which is the variance here, or a covariance out here. Yeah. So all these follow just from like the definitions of matrix multiplication and what a covariance means. Any questions on this? right. Covariance matrices are positive definite. Maybe I'll let you take a minute or so to think about why this is true. If you remember what the positive definiteness is from the last lecture, or just from your linear algebra background, then hopefully this isn't too bad. But maybe I'll let you get like a minute to think about this. Like, how would you show it? It doesn't take too much algebra. It doesn't take too many like lines of math. But you kind of have to have some insight. Yeah. Uh, yeah. So just remember what positive definiteness means. So, uh, did anyone get the full steps? We'll go through all the lines of math, but just seeing if anyone got through the full steps. Maybe 10 more seconds. Yeah, so there is a comment. Usually when you prove that something is positive definiteness, the you reduce the definition to something squared, and then it's always non-negative. Yeah, so something like that is always basically how you prove something is positive definite. All right, so here are the full steps. Let's go through this line by line. The first term is the definition of a quadratic form. So a quadratic form is anything of the form like vector transpose times matrix times the same vector. So it's like you're squaring something, but you're squaring, quote, squaring a vector. The intuition here is a little bit off, but hopefully that's what it means by quadratic form. So you sum over all the rows and all the columns, and then you get this. Going from the first line to the second line, that's just the covariance. So that's the covariance of scalar, random variables. So it's xi and xj. And then this thing here is also like the definition of covariance. We just express it in using the definition that we covered a few slides ago. And then this term we use linearity because you have a double sum over a whole bunch of expectations. So you just pull out the expectation. And when we're at this point, you can reassign your xi minus expected value of xi, just make that equal to yi. All right, and then get yj. And then the last line is like the double sum of yi, yj, zi, zj. And if you turn them into vectors, you get y transpose times x times z, and it's squared. So if this thing is a little bit unclear, you can try with just n equals 2, and then see how the math works out. So Yeah. Yeah. Oh, and then the last technicality is that this alone would just show that it's positive semi-definite. But if you really want to show that it's positive definite, you have to show that if this thing is equal to 0, it's only when z is 0. Yeah. So if it has an inverse, then we know that it's full rank, and then it's also positive definite. If you're, yeah, so I won't go into more of the details, but you can look at the notes that I linked to for today's lecture on the website, and then it'll explain these things a little more. But yeah, so again, this is all just math to make sure that you're familiar with and comfortable with linear algebra and probability. So like basically the most important math area for robotic. Yeah, and then we talk about single variable Gaussian, then more generally, we have multivariate Gaussian. So we have the probability density function of the single Gaussian, and then the density function for a multivariate Gaussian. So now we have to parameterize it by mu and a covariance matrix. So it's a mean vector and a covariance matrix. So that's the sufficient information to understand what this means. So yeah, I mean, technically, I really should have written like P of X semicolon mu of sigma squared. So just always remember that when you're dealing with Gaussians, you have to, assume you have some mean and covariance matrix. So does everyone see this term? Like the first part is just the normalizing factor. This is a determinant. So we covered that briefly last class. So the determinant is like the measure of some volume of this matrix. And then you have an exponential of this thing. So remember that this thing is a quadratic form of this matrix inverse, right? So it's like a vector transpose times matrix times that vector. So that's a quadratic form. And we already covered that it's positive definite. So, the inverse will also be positive definite as well. And then that means the term, like the quadratic form, is going to be positive, but we negate it. So it's always going to be like, it's always going to get, like the exponent is always going to get, much smaller. And then because you do like a 1 over exponential of this thing, then this thing will decay rapidly when the mean vector is far away from mu. So that's why it still integrates to 1, even though so basically that's why it integrates to 1. All right. Yeah, then integrates to 1 with this thing here. And if you want to visualize it, so usually as always it's easier to visualize in 2D. So if you look at examples in 2D with an identity covariance matrix, but we change the mean vector. And if you plot the density function, it'll look something like this, where this represents the first term in mu, and then this axis represents the second term. And if you look, you kind of have to look carefully in the slide, but if you have mu of 1 and then 0, then the mean where the peak is at is going to be like at 1 and then 0 here. And you can try to see where the coordinates line up, and then the peak is at the mean. So, and the same thing, like if you shift the mean mu to be somewhere else, then if you keep the covariance matrix the same and you change the mean, it's just like you're taking the distribution and then you're like moving it around without actually changing the local topology. Does everyone see how to derive this thing? Because sometimes it's also Yeah, so sometimes like different exams or whatever, they show like, here they curve, like what is a possible covariance matrix? Like I've seen that before in like undergrad, like probability or something. So, all right, so what happened when we try to change the covariance? So in all these cases, the mu vector is just zero. So it's centered at 0, 0. But if you make the covariance term go from like 1 in the diagonal to 0.6, so these are all diagonal covariances. So if you decrease the variance, the spread will decrease. So it becomes peaky like that. And then when you increase the variance of the two terms separately, then it becomes like a fatter distribution. And of course, the next case is what happened when you might have to change some of the things in the off diagonals too. So these are the off diagonal terms that describe the interaction between x1 and x2. So if you take a top-down view and then you try to do horizontal slices and then to plot those in 2D, if you have the identity covariance, it'll look like this. But if you have off diagonal terms that look like this, you'll get something that looks like this, where they're in some sense positively correlated. And so that's why you see it, going this way instead of like going this way. Yeah. So hopefully this is clear, like how these mean and covariance matrices lead to density plots that look like the above. Okay, so I see a question about, can you explain the density plot for the second two cases? Well, all right. So because the covariance matrix is like this, like all right. This is what the second covariance matrix means. You have 1 and then you have 0.5 in the off diagonal, but they're positively correlated. So like it's like whenever you whenever you increase one value, like you're increasing the second value, the first value is also increasing as well. And so it's like when you imagine the diagonal, this diagonal is like the direction where the peak is like shaping at. So I guess I don't have a better explanation other than the fact that if I try to visualize how it looks like, it'll turn out to be something like that. And you can also, like, if you're not convinced by this, you can also literally just program or sample from a 2D multivariate Gaussian and then just plot them and then see plot something like that. So that's another way you can get some more intuition here. Yeah, then yeah, I guess if they're even more positively correlated, then it's like when x1 goes to a certain value, it's very likely that x2 is like also going to be close to it in some sense. So you get peakier values. Yeah. I think that's my intuition. I don't know if it's the same intuition for everyone, but it's something I think about. Yeah, then there are other properties of Gaussians, like there's some formulas here, like again, you don't really have to memorize that. You should although put it in the cheat sheet for your midterm and then the final. So, or maybe we'll just give you the formula so you can save space on your cheat sheet. So let me know what you prefer. So yeah, so if you have like independent Gaussian, then you basically have the formula here for for the newer Gaussian when you try to sum them together. And again, it's always easier to think about a single variable example instead of a multi-variable one. So if you have like X and Y are the Gaussian, but not multivariate or not multivariate, then if Z is like the sum, then intuitively the mean of Z should be 3 because the mean of X is like 0, the mean of Y is 0, and then you just get 3, and then 3 is like the sampling point. Yeah, so just be aware of the independence assumption. So sometimes you can always disprove something by, if you have like a math question and then it says, is this thing true for two random variables for the sum? Then a common counterexample is set Y to be minus X or something. And then that helps you to catch many counterexamples in a bunch of math related questions for probability. All right, so in the meantime, we're going to talk more about like probability, but in the context that will be more like robotics focused. Now, we're going to be considering function over some time, or maybe random variables over some time. So we'll have t be time, and then x of t for some sensor, or if it's a random variable, then we'll sometimes write x with superscript or subscript of t. And yeah, so the concept of stationarity is just saying that does this function depend on time, or is it the same for all time steps? So like if you have the first process, v equals 1 plus w, and w is drawn from a standard normal, then this is stationary. It doesn't depend on time. But the other two things, they depend on time. Like v is this value plus some noise, but the t keeps changing. So it's not stationary. So it's stuff like that. All right. And that brings us to Markov chain. So a discrete time Markov chain is one where we're considering a random variable where we have xt, where t varies from 1 up to something, and it represents a time step. And the Markov property means that the probability of moving from 1 to the next, the only probability you have to think about is the one just before it. So the probability of t plus 1 conditioned on everything here, you could just ignore everything up to xt. Yeah, so that's what the Markov property means. And it's also really nice because if you remember how to factorize a joint probability, you have this term here. It's like a joint, and then you can factor it into this using the Markov property. But if you didn't have that, then you would have to have more things. Like you would need to have p of x3 conditioned or given x2 and x1. So that's just the definition of the chain rule of probability. But if you have a Markov property, then you can ignore some of those variables. And that greatly simplifies the math. But you really do have to check that it's actually true. So again, when we assume that something is Markov, it's like a modeling assumption. It may or may not be true. But if it is close to being true, then maybe it's okay to assume because it greatly simplifies the math and algorithm and other things. But yeah, just be aware that the Markov assumption might not be true. So it depends on what problem you're considering and the model that you're approximating and so on. Yeah. All right. And one way to reason about Markov chain is to think about transition from one state to another. So you can think of like a transition matrix showing what is the probability that we go from like x1 to x2 or x1 to x3 or so on. And that tells them transition probability. And so here's an example of a Markov chain. Now, here we're going to assume that x1, x2, and x3 represent random variables that are the battery is full, the battery is low, the battery is empty. I mean, in practice, you would have to discretize it into different ranges, but like this is, just think of this as the thing that we're dealing with. With a Markov chain, we can go from x1, we can repeat at the state for the next time step, but we can also like proceed to the next one. And with this transition probability, we're going to assume that we can only stay at our current state or move to the next one. So only one of those two things can be true. And visually, it looks something like this, where you have like A is like the probability that you repeat. And then 1 minus A is probability of going from x1 to x2. And what is the probability of x1, x2, and x2? And here, the notation here really means probability that at the first time step we're at x1, probability at the second time step we're at x2, and the probability at the third time step we're also at x2. So, and yeah, if you work it out, then it'll be something like this, where any question before I show a video to finish up things? Yeah. What's the question?
Can you speak up louder, please? Is there a typo in the last?
Yeah. So what it's more like what by the notation I really meant at the third time step, what is the probability of going to x2 conditioned on staying that we were already at x2? So it's like this thing here is like probability that we stay at x2 given that we're at x2, probability that the state at the next time step is x2 given that the current one is x2. Yeah. I think the better way is, I think I can try to rewrite the notation to make it a little bit more clear, but that's basically what I implied. Yeah, then this is also the same question that I see here. Yeah. I think I can go back to the slides and then try to clarify the notation here. We just have 2 minutes left, so I'll just conclude with this video. So hopefully it'll be a good conclusion to the lecture. So what this is showing is it's showing a DARPA robotics challenge. So DARPA is a government agency that funds a lot of robotics research. So I mean, I'm trying to get funding from DARPA, so you can kind of see like why that's true. And what I want to show or emphasize here is that robots have to deal with a lot of uncertainty. So if we're trying to get robots to do something like, even as simple as something like opening a door, there's always some kind of uncertainty, and when it takes an action, what will it look like after that? And you can see that there's so much structure that humans have to put in to make sure that robots succeed. Like you have all the support that you need to you need like all this the support team on the robot to get them to handle uncertainty. So and sorry. So let's see. Well, we're basically out of time, but there's just a handful of slides that I wanted to cover, so we'll just cover them next week. So for next week, we'll cover the remaining of this plus Python and ROS tutorial. So most of you don't need a Python tutorial, but we do cover ROS. So hopefully that will be clear, then we'll cover more on Bayesian networks. So see you next week then.